So, as I said, this morning we will cover inverse differential kinematics and statics and force transformation. So inverse differential kinematics is in fact the opposite of what we have seen last few times. So given a desired motion at the end effector level, in particular, why not, a velocity, how do we generate a velocity at the joint level where the actuators are placed, so where we command motion, in such a way that we realize that desired velocity. And this is something done at every configuration. So while moving, you have to repeat this computation on and on. Statics and force transformation instead is the transformation of forces and torques applied at the end effector or at the task level, more in general, as we now are familiar with, into joint torques at the joint level in a condition that the system is balanced. And we will see different formulation for this. So now a few comments here on the fact that when I say end effector velocity or task velocity, I'm intending this in a generalized sense. So there could be linear and or angular components, so whatever you're working with in the task space. For instance, in the planar case, we could have two components which are linear velocity in the plane xy, and one component which is an angular velocity, it's a scalar, around an axis which is normal to the plane. So we have three components, or just two, or 6 components, or m component in general of a mixed type. So generalized velocity, but from now on, I will skip this generalized adjective. So given a desired velocity, and this is an instantaneous problem, like we said, we've seen that the mapping of joint velocity to Cartesian or task velocity is also an instantaneous problem. Same in this case. We have to find one or more joint velocity vector that realize the task. So this is the relation that we will use. Now, this looks like the geometric Jacobian. It could be the analytic Jacobian, the geometric Jacobian. We don't care. So I skip the subscript and just use Jacobian collectively. So generalized velocity is in the task space, Q dot is the unknown, we are in a given configuration. And so the problem is quite simple if we assume that the Jacobian is square, so we have as many joint variable, joint velocity in this case, as task variable, task velocities. So the Jacobian is a square matrix and it's non-singular at the configuration where the robot is at the moment. So in this case, the solution is unique. So we have a Q dot, we have to invert this matrix in real time and generate the joint velocity. And this will guarantee that we execute the desired task velocity V. There's no other way of doing things. Now, indeed, we can imagine that we move with this joint velocity, so the configuration of the arm changes a little bit. We apply this velocity for a sampling interval, which typically is 1 millisecond or less or more, depending on the control architecture that you're having. So you're moving for a while, so you're changing configuration. Now, the desired velocity at the task level may change or may be the same, doesn't matter, but your configuration has changed, so the previous computed joint velocity is no longer the correct one to execute that Cartesian velocity. So you have to recompute the Jacobian, you have to invert this Jacobian numerically at the new configuration, and you have a new velocity, and you go along. This is a continuous process that has to be done in real time. Now, I could stop here if there were no problems associated to this inversion. So the problem are essentially two. What happens if we have a square Jacobian, but we are near a singularity? We have seen already that singularity corresponds to loss of mobility at the end effector level. So there could be direction where we cannot move with the end effector instantaneously. So if we assign a velocity in that direction, what happens? We cannot solve this problem. Or even close to singularity, even if we can invert the matrix, we typically generate large velocity q dot, so too high for the capability of our actuators, so we were not able to execute them. And I will illustrate all these points, all these issues on a simple example, again, with a 2R planar robot, but I think it's clear enough to understand what's going on. So what do we do when we are near or at the singularity? Okay. The other problem is, what if the Jacobian is non-square, so that the inverse, it's not defined? So we have to generalize the concept of inversion, and we will see that we can do this in a number of ways. Essentially, for this course, we will limit ourselves to the use of pseudo-inverses. Okay, so these are our two problems. And I collectively define finding solution to this problem by saying that we would like to have a more robust inversion method. So not just using the inverse as such, but a method that handles, if necessary, otherwise we stick with j to the minus 1, all this situation. So before proceeding with an example that will occupy ourselves for a while, let me make this remark. So we have seen inverse kinematics problem, and these are essentially an offline static problem, giving a pose for the end effector, find the configuration. At the end of the problem, with numerical methods in particular, we have mentioned that we can repeat this problem several times if we have a sequence of post data. And we can also associate to each iteration of a numerical method some kind of motion of the robot. So the initial configuration, the initial guess for our inverse kinematic is where the robot is currently, the real robot is currently placed. Now we give a small increment to the task variable, and we solve a new problem, starting with this guess. And then we repeat this over and over. Now, how is this related? So the repeated solution of a sequence of inverse kinematic problem, how it is related with joint velocity inversion? In fact, it is close. And in this slide, I would like to use both the direct kinematics, which is now written in the analytic form, and the differential kinematics, and for the time being, you can consider that this is the analytic Jacobian. How are they inverted? What is the relation between these two? So suppose that we have, we are in a given configuration, we are a given pose R, and now we would like to modify slightly by a small amount where we are in the Cartesian space or in the task space. So we move from R to R plus dr. Now pay attention, the differential kinematic is written in a slightly different form, so you don't see velocity just because I eliminated the division by dt, but if you divide by dt, you have r dot on the left-hand side and jrq q dot on the right-hand side. But let's work with small increments, so infinitesimal, but I mean, small enough. Okay, this is why I'm writing the new task variable is the value moves from R to R plus dr. Now we can do two alternative things. One thing is, well, this is a new value of R, so we increment the task variable, and we have a new problem of inverse kinematics. So we have to find a q such that f of r of q is equal to r plus dr. Indeed, we may have a closed form solution, so this is just calling the analytic formula once more, Or we may wish to use a numerical method, so we have to start our iteration of the gradient or Newton method. The current Q is close enough to the good one, because with the current Q, we are at the value R for the task variable. Now we have incremented this, so this is a good initial guess. So we solve this problem, and we have a new configuration to provide to our low-level controller. So you should move to this configuration now. Okay? So this is purely with inverse kinematics. What is the alternative? The alternative is to reverse the two steps. So I have a dr, so a variation of the task variable, if you wish an r dot, but just for a small interval, so a dr, and we invert the differential kinematics. Suppose that the Jacobian is non-singular and square, so that otherwise the same problem occurs that we mentioned before, and we will see what happens then. So we invert the Jacobian, we multiply by dr, and we have an increment dq. And now, from the current configuration, we were in q. In fact, we inverted the Jacobian in q. We give an increment, so a new position q, which is q plus delta q that we computed, and we say to the local controller, go to this position. Or just say, make this increment at the velocity level for a small amount of time. Okay? So you see that the result is practically the same. I'm mentioning this because there are robots that do not use, a commercial robot, I'm meaning, that do not use the Jacobian, so they do the first path in order to compute the new configuration. And robots which use instead the Jacobian, of course, they have also the direct kinematics. This is always present, but they use this differential inversion, okay, scheme. Okay, so now let's consider this particular case. I have a tour robot. The linked length is 1 unit, 1 meter, whatever. So equal length. And we are given now, so the workspace is this circle that you see. The base of the robot is placed at the origin. And when our robot is stretched, its end effector is distant 2 units, so 2 meters from the origin. So this is the external boundary of the workspace. We know that at that position, we are singular, so on the boundary, but we are also singular and in a different way. So we have an infinite number of solutions when we ask the robot to place its end effector at the origin. In this case, L1 is equal to L2. Okay? So let's now do some motion in the sense that we have an initial point in the Cartesian space, the start, and a final point, end. And these are connected by a straight line. So this is a path. There's no timing law assigned to this. We will see this clearly, this separation, when we deal with trajectory planning, which will be our next topic from the theoretical point of view. So it's a straight line going from a point which is quite close to the boundary. So where the Jacobian it's not, it's still regular, so, but it could be close to a singularity, and crossing the whole workspace and getting to the end point, which is similarly close, not as close as the start point to the boundary, but again. And we decide to do this motion at constant speed. So we give a timing law, a very simple timing law. We will almost never use this type. So constant speed right from the beginning. So there's no transition from rest to this value. This is something that the robot will not be able to do, but at this stage we don't care. So 0.6 meter per second for 6 seconds. So we have to move from start to end in 6 seconds at constant speed along this straight line. And this is the task for the end effector. Now, if we invert the Jacobian continuously, and of course, I'm doing this computation, this is a simulation, it's done with let's say 10 millisecond increment, so you don't really see the difference in a continuity. And on the right-hand side, you see a stroboscopic view of the motion. The green configuration is where the robot starts. So it's on the x-axis. And then it moves by folding itself. It's like a compass, no? It's closing itself about the midpoint. Let's see if I can, okay. At this stage, where my pointer is, you see that there's a kind of a reconfiguration. So the robot, in order to keep the end effector on the line, and if you can interpolate the end effector position, you see that this will be the line. There will be a sudden reconfiguration. So the elbow comes down, and then the compass opens itself again until it reaches the final configuration where the end effector is in the end point. And you see that it's a bit more folded than at the beginning. In fact, the end point is closer, is farther from the external boundary than the start point. Okay, so this is what happens if I'm applying j to the -1 continuously. Of course, this is a stroboscopic view. There are only samples of the many configurations that the robot is assuming. If I would draw all of them, I would see just a coverage of the area. So I would not recognize the single individual configuration. So these are only 10 extracted from the full motion. So no problem here. And let's look at evolution. This is a simulation made in MATLAB. Also, the plots are all made in MATLAB. So you see that the two joints are moving, Q1 and Q2. On the top right figure, you see the velocities, so Q1 dot and Q2 dot, which are continuously computed through inversion of the Jacobian. And you can recognize that right at the center of the motion, around 3 seconds, there is a sudden increase of the velocity of joint 1, which corresponds to this rotation of the structure around the origin. Now, on the bottom part, there are two other plots that needs to be explained. So on the left-hand side, I trace the minimum singular value of the Jacobian. We mentioned that we need a measure from singularity. You may use, in this case, the determinants, but the determinant is 0 when the robot is singular. But in this case, but it's not a good measure of distance. So you see that we start with a value at the beginning, which is close to 0. In fact, the arm is almost stretched. Then when the arm falls, the minimum singular value increases, so we are distant from the singularity. At the midpoint, since we are getting closer to the origin, which is another situation of singularity, you see that there's a reduction again, and then the motion is almost symmetric. And in fact, you end up with a final value at time equals 6 seconds, which is higher than the value that you had at the beginning, and also to the minimum at the center. Okay, so this is in order to check if we are getting close to a singularity. And finally here is just the norm of the Cartesian position error. In fact, we can recompute every time. Once we give a value q dot, we move, and then the end effector should still be on track, so on the straight line. And this is just a measure of how the error evolves over time. And in fact, it's practically 0. Don't be disguised by MATLAB, who automatically resize the scale. The full scale here is 10 to the minus 10 meters, so practically 0 error. Okay, but we will trace this numerically here. So let's move to a slightly different modified problem. So same story, same start, but the end is a bit more lower, so that the straight line gets closer to the singular point in the center of the workspace. So we are close to a singular situation. The angle that this line is making with respect to the positive x-axis, it was 170 degrees before, now it's 178. Indeed, since we are starting on the x-axis, if we make a straight line which is horizontal, so with respect to the positive x-axis from start to end, I would have alpha equal 180 degrees, and then I would cross the singular point. Okay, but I will not do that. See, we are 2 degrees off now, but 2 degrees means what in terms of Cartesian position? Now, 2 degrees is a small angle, so you can approximate sine and cosine. I mean, sine of an angle with the value of the angle itself. You express the 2 degrees in radians. So this is about 100 of a radians. The distance is 2, so the radius is 2. So we are about 2 centimeter above the origin when we are crossing the origin. This is the path, okay? So again, we run the Jacobian without any, the inversion of the Jacobian without any prevention. We just do the same as before. The time is the same, the speed is the same, so the task has not changed much. And it's in fact, the length of the path is equal to the case before. So if we have 0.6 meter per second for 6 seconds, we have 3.6 meter path length, which is a bit less than 4 meter, which is the full diameter of the workspace. So we are still inside the workspace, in fact. So the stroboscopic view looks similar, but you can see that this is sampled uniformly. So these are configurations sampled uniformly. You start with the same configuration as before. You end up with a slightly different configuration because you're more close with the endpoint to the x-axis. But in between, the last configuration which has elbow up, let's say, and the one that has elbow down, there's an empty space. It means that this motion has been executed while getting close to the singular point at the center of the workspace with a high speed, so that you suddenly change configuration from top to bottom. In fact, this can be seen in the following plots. So from the position, you don't notice much, although there's a large variation close to the center. In fact, if you look at the velocities, in particular, the velocity of joint 2, not of joint 1, not of joint 2, you see that from an average value of 90 degrees per second, you have a peak which almost reaches 800 degrees per second. And for a few instants, when you're getting close to the singularity. And in fact, if you look at the measure from the singularity, you see that you started with 0.3 as before in the same configuration. The start point is exactly the same as before. And then you moved inside the workspace, so the distance from the singularity as measured by the smallest singular value of the Jacobian, which is kind of related to the eigenvalues of this matrix. We will see this explicitly. Now, when you're getting closer, now you get much lower than, you get much lower here. Sorry. Okay, wrong button. So here at the center, you get much lower than before. So you're getting very close to singularity, and then again, back over, and then you stop with a kind of regular configuration at the end. So still, you can say, am I able to command almost 800 degrees per second? In this simulation, there's no limitation, so nothing happens except to accept such a large joint velocity. From the positional error, this large velocity gives a bit of a hit to the integrator. So we have 1 order of magnitude greater error, but still 10 to the minus 9, so completely negligible. So, but in order to make things more realistic, this is exactly the same situation as before, but now I added in the simulation the presence of a joint velocity limit. So the actuators cannot provide more than 300 degrees per second. So we saturate any command that is larger than 300 degrees per second, plus or minus. Okay? So this is the execution, same angle, 178, so getting closer to the singularity. From the stroboscopic view, you don't see any changes, in fact, because this it's too it's not accurate enough to describe what's going on, but nothing happens at this level. But if we look at the plots, again, Q1 and Q2 have a similar profile, but here you see that you saturated the Q1 dot value for, say, 0.2, 0.3 seconds around the center, when it was going to the peak, and now has been saturated to the maximum value, 300 degrees per second. Nothing special for the closeness to the singularity, but here is what matters. As soon as you are not able to command the desired velocity that would execute the right Cartesian velocity, then you have an error. With the wrong velocity, with the saturated velocity, you will have an error at the end effector level. In fact, you have an error which is practically 0 before, 10 to the minus 9, 10 to the minus 10, and then all of a sudden increases, and then if you don't react to that, you have a position error which remains as large as 6 centimeters. Okay, we have made a big jump because of the saturation of an inversion of the Jacobian, which would not take into account the fact that there's a limit, and if we're getting close to a singularity, we would have very large joint velocities. Okay, so we need to do something here. So one thing that can be done is to use a so-called damped least square approach. So to damp out this joint velocity. Now the problem is formulated as an unconstrained minimization. So an optimization problem where we minimize some function. So remember, we are at the current configuration Q, so you don't see Q here, but in fact, all these computations are repeated at every new Q, so every millisecond, okay? So you want to minimize this function, and the function is made up of two terms, two norms. One is the square norm of the error on the velocity task. So you would like to find a Q dot, which is your unknown here, such that JQ dot is equal to V. So, but you relax this equality, but saying that you like to minimize the error on this velocity task. But this is not the whole story. You add to your objective function another term, and the relative weight is given by this factor lambda, which is positive or 0, and is 0 if you don't care about the how large is the joint velocity that you're obtaining. But if you care, you introduce this term, which will increase the value of the objective function in case you are solving, inverting just the Jacobian and getting very large values. So this is forbidden by this. You see that we are not saying we are inverting the solution, we are just saying we find the Q dot that minimizes this quadratic function. The quadratic function is positive definite, so the minimum is unique, and in fact take this form. And I would like you to prove that this is the result. How would you get this formula? There are, in fact, two expressions of this formula. How do you get the first one? So lambda times the identity matrix of dimension n, if n are the joints of the robot, plus J transpose J, everything to the minus 1 times J transpose times V. How do you think you would get this type of result? Any suggestion from home? Well, the keyword is already on the screen. It's the blue text, unconstrained optimization, in fact, unconstrained minimization. How do you minimize a function? You make the derivative of this function, you compute the derivative with respect to the variable, in this case of Q dot. This is a quadratic function in Q dot. The derivative is a linear function in Q dot, and you set this derivative to 0. And then you find a stationary value. It could be a maximum or a minimum, but here this is quadratic and positive definite, so if you zero the first derivative with respect to q dot, you have a minimum, okay? And then you solve the linear equation and you find this. And this can be done all the time if lambda is positive. That inversion, lambda, that matrix, lambda identity plus J transpose J, is always invertible. Why is that? Because lambda times the identity is a positive definite matrix, so invertible. J transpose J is a symmetric semi-positive matrix, always. So if you add a semi-positive to a positive definite matrix, you have a positive definite matrix, always, and a positive definite matrix can always be inverted, okay? Now, this formula has a second expression where things have been moved around. So instead of writing the inverse of an n by n matrix and then multiply by J transpose and then by V, we multiply J transpose by the inverse of an M by M matrix. And if M is equal to N, then of course I didn't get any convenience in doing this. But if M is strictly less than N, like in the redundant case, the second formula is much more convenient. Of course, I would like that you prove that these are equivalent, and this is a nice trick in working with matrices, to see that the expression on the left-hand side of the yellow arrow is equal to the expression on the right-hand side. And we call this expression, both of them, but in particular we'll use mostly the second one, dampedly squared Jacobian, or damped Jacobian. Just another way of inverting things, of finding from a given V, a desired, from a desired V, sorry, a joint velocity that will try to realize the task. Pay attention, try to realize the task. Now this dampedly squared can be used no matter if the Jacobian is square or non-square. Okay, so this expression stays in any case, in particular when we have a redundancy, so n is larger than m, we say that the right-hand side expression is more convenient because you invert. For instance, if you have a robot that has a task which is two-dimensional and the robot has 8 joints, in the first case you would invert an 8 by 8 matrix. In the second case you would invert simply a 2 by 2 matrix. So I guess that we are all agree that this is more convenient. Now, when we are, there's a price in using this dampedly squared. The price that we paid is that as soon as lambda is strictly positive, then we will make an error. We will make an error and we will trade off the error in executing the desired Cartesian velocity with the advantage of having limited joint velocity, so that they may stay within some bounds, and so they could be feasible. Now, so this means that if we are far enough, and far according to some metric from singularity of the structure that we have analyzed already, then we would set in this formula simply lambda equal to 0. And then we know that we will be able to execute whatever V is being requested. Of course, if we're requesting a large Cartesian velocity, then we will have a large linear velocity. There's a scaling factor which migrates directly. So if we look at the expression of JDLS, dampedly squared, and we set lambda equal to 0, for instance, in the second expression, we find J transpose plus JJ transpose to the minus 1. Now, if J is square, then the inverse of the product of JJ transpose, the inversion can be distributed on the two factors. So you invert the order of the factor and you take the inverse. So JJ transpose to the minus 1 is equal to J to the minus transpose, so the inversion of the transposition, times J to the minus 1. Since we have a factor J transpose in front, this ends up with being J to the minus 1. Okay? It's a complex way of writing J to the minus 1, but is in fact what you get. If instead you have a redundant case, so the matrix J is M times N with N larger than M, so it's non-square. Nonetheless, JJ transpose is an M by M square matrix. Since you're far from singularity, this will be a full rank matrix. So you can invert and then multiply by J transpose. You get an N times M matrix, so N rows and M columns multiplied by the m-dimensional velocity vector V. It provides you the joint velocity. And this is nothing else than the pseudo-inverse of the matrix. It's the definition of a pseudo-inverse of the matrix that we will encounter in a short moment. Okay, and this is when we are far enough. So lambda can be taken to 0. When we notice that our measure of distance from the singularity is getting dangerous close to 0, then we introduce a lambda, and the price to pay is, so we reduce the amount of joint velocity in norm, but we make an error, epsilon, I call it epsilon, which is, pay attention, an error in velocity, not in position. Of course, this error in velocity will generate an error in position later on, as we have seen when we introduce the saturation of the joint command. And the error, you can check that the expression of the error is lambda times the inverse of the lambda I plus JJ transpose matrix times V. So it increases with the velocity, of course. It doesn't increase so much with lambda, because as you can see, if you imagine that the second term is a scalar, you have lambda at the numerator and lambda at the denominator. In fact, we will see in the second course of robotics, when we deal mostly with all the techniques for redundancy resolution, that there's a peak of this error somewhere in between, and then this goes back to 0 when lambda goes to 0. Okay, so we have an error, but we have always reduced, so dampened joint velocity, and this is the reason why we are doing this modification. So let's consider this comparison, not with the previous case. I moved farther closer to a singularity, so the straight line is almost horizontal, so it's making 179.5 degrees angle with respect to the positive x-axis. Otherwise, the task is the same, constant speed 0.6 meter per second for 6 seconds. So I'm going from one point to the other of the workspace, more or less in a symmetric way. What ensures us that this matrix works like a Jacobian, and so it's super, okay. No, it does not ensure that it works like a Jacobian, in the sense that if I could invert the Jacobian or pseudo-invert the Jacobian, I would generate exactly the desired velocity. Here, I know for sure that I will generate an error, okay? So the trick is, what is the best compromise with the lambda? So it's lambda different from 0, but not too large, so that you keep the joint velocity limited, and still you're getting close to what you would like to do. And I will, this is the purpose of exactly this other simulation. So if you compare the motion, now I don't show in this slide the stroboscopic view, but we will see it immediately after. You see that when you're inverting the Jacobian full stop, still you're not considering the joint velocity limits, so you assume that you can implement whatever large joint velocity you get, you go straight on the path without doing any error. While with the dampened least square, you see some bumps around the origin, which means that for a short while, you get the wrong velocity, both in intensity and in direction, but then you recover. Why you recover? Because I made a trick here, made a trick which is very common. Namely, I used a control scheme on top of that. So I added a correction which is based on the error position that I'm realizing. You don't need this correction in the first place because you assume that you're executing correctly the velocity, so there's no need to recover some induced position error. So now look at the stroboscopic view here. On the left-hand side, same situation as before, from elbow up, then all of a sudden, close to the singular point at the center of the workspace, you have a huge variation, okay? But still the end effector is kept on track. On the right-hand side, you see a completely different solution. So for the first part, it's the same, but when we are getting close to the singularity and we are activating the damped least square method, so the lambda becomes different from zero, and the way in which it becomes different from zero may be introduced in a smooth way so that you don't perturb too much the solution. And you see that we get out of the singular region in a completely different configuration. You see, still with elbow up. So it's a completely different solution, okay? Now, let's look at the velocities, okay? First, the evolution on the left column with the exact inverse, on the right column with the damped least square. So the position are different, of course, not in the first phase. The first phase is pretty much the same, although the scale is different. So, but you can notice up to a half time of the motion, so 3 seconds, the blue line is going down, the red line is going up, then a different behavior occurs. Now, if you look at the joint velocities now, you see on the left-hand side, you have a peak which reached now 2000 degrees per second, so certainly not realizable, but I wanted to keep this for comparison. While look what happened with the damped least square. We have joint velocity which are around 80 degrees per second, so fully normal, like before. The price to pay is that we have an error, okay? But certainly the right-hand side will be implementable and the left-hand side not. So the question is, am I staying on path? So can I use this as if it was the right Jacobian, although I'm ready to compromise with a small error? So let's look at the error. Now, on the left-hand side, again, the large peak, this is a simulation, so I'm assuming that I can realize this velocity in the integration of my differential equation to get the new position. I have an effect. In fact, you see that the error is still negligible, but from 10 to the minus 10, we move to 10 to the minus 9, now 10 to the minus 8, which means that there's something affecting the accuracy. But anyway, zero error. Now look what happens. We have 25 millimeters error peak close, so zero error until the lambda parameter is kept to zero, so that we are doing with the damped least square method, but still equivalent to the j to the minus 1 method. Now we have some error. When the singularity region has been crossed, we switch off the lambda, so we return to the previous solution, but we correct the command v, the nominal command v, so the desired velocity along the path, with an error term which is proportional by a gain which is positive, let's say diagonal matrix 2 by 2 in this case, proportional to the position error. So to the difference between where we are with our end effector while we're moving with q, so p of q, and the desired pd, which is nothing else than the velocity path integrated and generating a straight line, okay? So it's a point that moves along the straight line. So we recover by this feedback. In fact, this is a control, this is kinematic control. We will see this as the last topic. The error goes back to zero. So at the end, we tolerate for a small interval, a small error, 25 millimeter. Remember that this is a 2 meter long arm, okay? But we never generate unfeasible joint velocity that would not be executed in practice. If you look at the minimum singular value of the two situations of JJ transpose, in fact, and of lambda I plus JJ transpose, which is the matrix that you invert in the damped least square, well, they are pretty much the same. If you're inverting the Jacobian, then you have at the center this small blue part that goes pretty much close to 0, while you see that introducing the lambda will resume the distance from singularity. Okay? This is just a measurement of how good you can invert things. And what is the profile of lambda? The profile of lambda is the one that you see in blue in the last plot. So it's kept to 0 until you get close enough. Now, how close and how large you will get to lambda, this is, again, needs to be studied a little bit for each robot, but for each singularity, but this is something that can be done. So you increase it up to 0.1, not much, and then you bring it back to 0, okay? So with this evolution of this parameter is called damping factor. In fact, in the damped least square, you obtain this result. Okay, what else can be done? What else can be done? In particular, we have seen that damped least square is for robustness with respect to singularities and can be used both if we have a square Jacobian, so m equal n, and when we have a non-square Jacobian, so in the redundant case. In this case, we can use also another method, which is called the pseudo-inverse, which sometimes it looks like the damped least square. Here, we find the Q dot by solving now a constrained, not an unconstrained optimization problem. And this problem may look like this. So we look for Q dot. Instead of saying we invert the JQ dot equal V problem, because we cannot invert it, because J is not square. So we keep it as a constraint, JQ dot equal V, and we said, okay, since we have many joint velocities that may realize this, we look for the one that minimizes the norm. Okay? You see that there is a reason for doing this. Now, we want to keep low command for doing the same job. We don't want to spend energy or velocity for doing the same Cartesian velocity v. Okay. Now, however, this formulation has some criticality because there are cases where J, still non-square, may lose rank, as we have seen, so we may lose mobility, and we may not solve this equality. So if we keep this as an equality, then we may get no solution at all, because we are not able to satisfy the equality. So what is the sense in minimizing the norm of the solution if we have no solution at all? So there's a slight modification of this formulation, which covers the fact, the situation of having a constraint explicitly and being able to satisfy this constraint, which is the case when the Jacobian has full rank. But this next formulation is more general. So it covers also the situation where V cannot be realized. So we are still minimizing the same objective function, so the norm of the joint velocity, but looking for not using any value or not using just the value that satisfies JQ dot equal V, which may be an empty set. So we're picking up joint velocity from a special set, which is the set of n-dimensional velocity, because we have n joint, that minimize the norm of the velocity error. Indeed, we would like that this norm is 0. If possible, we will keep 0, and then we will resume the previous formulation. But this holds, this formulation holds, also if we are not able to satisfy correctly the velocity v. Why? Because v is not in the range of the Jacobian. This is our condition. So we have lost mobility because we are in a singular situation. We have not full rank. So we are not able to execute some velocity. Okay? Not all velocity, but some velocity depending on the direction. So in this formulation or in the other, when we can satisfy the velocity task constraint, the solution has this form. Q dot equal pseudo-inverse of J times V. As simple as that. Okay? Now, what is this pseudo-inverse? I'm coming there in a minute. Now, there are two situations that we should be aware of. If, as I said, the Cartesian velocity, the task velocity, belongs to the range of the Jacobian in that configuration, remember, everything is done at every configuration. So in a discretized version, every millisecond, in a continuous version, at any time. Okay, of course, continuous versions are not feasible. So if V belongs to the range, then we can satisfy the constraint JQ dot equal to V because V is feasible. So this solution will generate the desired task velocity V. Otherwise, if V does not belong to range of J, so there's no way of choosing Q dot that will guarantee this. So we have to accept some error. So what does the pseudo-inverse? So if you plug in this velocity Q dot, so J pseudo-inverse time V, into the differential mapping, so multiplied by J, so J Q dot with this Q dot is J pseudo-inverse B, the result is called V perp. You can use whatever symbol, just to use a symbol. And this V perp, solution of the pseudo-inverse problem, minimize, in fact, the error norm on the joint velocity. Of course, you cannot bring this to 0, but at least you know that you minimize. And not only you minimize this, by the very formulation, you're minimizing this velocity error while minimizing the norm of the solution itself. So you're minimizing at the same time two things. So the minimum norm in terms of less effort at the joint level, while satisfying at best the Cartesian velocity task. So this is also called the orthogonal projection of V into the range of J. So let's see how you compute the pseudo-inverse. So the pseudo-inverse, given a generic matrix, no matter if it's square or not, no matter if it has more rows than columns or more columns than rows or equal number, then it's the unique matrix. So given a matrix J, this is the unique J pseudo-inverse, J plus, how do you want to call it, J dashed, whatever, that satisfies this four relation. So this four relation define in a unique way the pseudo-inverse. So if I give you a matrix J, and then I give you another matrix saying, this is the pseudo-inverse of J, and you don't believe me, then you should check if these four equations are satisfied. If they are satisfied, then this is the pseudo-inverse because the pseudo-inverse is the unique solution to that. Okay? Now, if you look at this, the first two are like a majority, a democracy vote. So if you do the product twice J times J plus, you get J. If you do the products twice J plus J, you got J plus. The second two equations are very simple. You say that the product of J plus or vice versa are symmetric matrices. Okay? These are the four defining conditions. Now, there are cases where you get an explicit expression for the pseudo-inverse. In fact, when the matrix J has full rank. In particular, if it's square, so M is equal to N, and has full rank, so this means that it's non-singular, the pseudo-inverse is the inverse. So this is the most natural generalization of an inverse. In fact, if the inverse exists and you plug in J to the minus 1 in place of J plus in this four equation, you get that they are satisfied, and so this is in fact the pseudo-inverse. The other interesting case is related to the damped least square if when you have redundancy, so more joints, more degrees of freedom than task variables, so M is strictly less than N, but you have a full rank J. So you can cover any desired task velocity V, which is M-dimensional, because of the full rankness. So you are not in a singular situation, even if the robot is non-square, so the Jacobian is non-square. So in this case, the pseudo-inverse takes this form, J transpose times J transpose to the minus 1. Because of the full rank of J transpose is a M by M non-singular matrix that you can invert. And if you plug in this expression into the four defining equation of pseudo-inverse, they are satisfied as identities. So this is the pseudo-inverse. Finally, there's another case which will be interesting in the second course of robotics. There are cases where we try to solve more equation than unknown. So they are over-constrained linear system, still we can define a pseudo-inverse. And in that case, if the coefficient matrix is full column rank, in that case, so m is the number of equation, n is the number of unknown, n is strictly less than m, but the rank of the matrix is n, then you see the reversed version of the previous equation. So you multiply J transpose by J, which is the small dimension matrix. This is invertible, post multiply by J transpose, and this is the, again, the pseudo inverse. So all these are cases where I can give you an explicit expression. What if we are not in the full rank case? But in this case, we still know that the pseudo-inverse always exists and is unique, but in order to compute it, you have to do it numerically. Now, you cannot have an explicit, although complex form like this. So you have to use the singular value decomposition of the J matrix and then do some operation. We will not go into this detail, but please know that the singular value decomposition is an instruction in MATLAB, for instance. So you can do the singular value decomposition of J and look at the minimum singular value, and this is a distance from the singularity. It's the one that I plotted in the previous slide. And the pseudo-inverse, MATLAB has an instruction which is called inv, which does the inversion of a square matrix, and the pim is the pseudo-inversion of any matrix, square or non-square, which does exactly this, but in a numerical fashion. And inside the pim, if you look at the code, which can be seen in the MATLAB, it calls the singular value decomposition as well. Okay? So let's look at one numerical example of this. Again, the two are robot, equal link length equal to 1, and let's put ourselves into a singularity. So Q2 equals 0. Remember that determinant of J in this case is L1 times L2 times sine of Q2. So this is sine of Q2 is the determinant. When Q2 is 0, of course, the determinant is 0, and the matrix loses rank, and it can only lose rank once because it's a 2 by 2 matrix, can never become a 0. So it has rank equal to 1. So this is the Jacobian when, in all this condition, when we have set Q2 equal to 0. In fact, it's a function only of Q1 with cosine and sine. And if we put the robot in a generic Q1 configuration with Q2 equal to 0, so the arm is fully stretched, then we can decompose the Cartesian space, the two-dimensional space, into two complementary directions. One is the range of J, and the other is the null space of J transpose. And we know already from our analysis that the mobility is lost exactly in the NJ transpose direction, while we can still execute any velocity which is in the range of J. Okay, so if I give you a V which is in the dashed red line, then I should be able to execute this, even if I cannot invert the Jacobian, because the Jacobian is singular. In fact, I can use the pseudo-inverse, which is still defined and will generate exactly that solution. Now, one more comment on the forbidden velocity direction. So this is where we lose mobility at the end effector level. Now, you may think, well, it's obvious that I'm losing, that I cannot execute a velocity that goes outside, because I'm at the border of the boundary, at the boundary of my workspace, so I cannot go outside. But this is not really related, because this is a direction. So I cannot go outside, and this is obvious. But I cannot even go inside with a non-zero velocity in the direction pointing to the center, which is surprising. Why is that? Because that is exactly a velocity that I cannot execute. Now, the pseudo-inverse of J in this configuration, whatever Q1 is, so I can give you an analytic formula here. How do I find this? Well, there's an algorithm by Greville doing computation in an algebraic way, but if I give you this is the pseudo-inverse, what would you do? You would check the 4 defining properties. And in particular, if you do the product J plus, you get this result. So not the identity, not even a diagonal matrix, but a symmetric matrix. So this is correct. If I do the reverse product, I get again a symmetric matrix and wonder, without any dependence on Q1. Okay? Now, if I pre-multiply the first by J pseudo-inverse, or pre-multiply the second by J, or post-multiply the first by J, or post-multiply the second by J plus, so I'm getting this dominance expression, you can check by yourself that I will recover J or J plus. So also the first two relations are satisfied. So this is the pseudo-inverse. Now suppose that I have assigned a desired velocity in that direction. Can I realize this or not? One says, well, it's not in the range, I cannot realize. Correct. But in fact, I can realize a part of this. What? The orthogonal projection. The orthogonal projection on the range space by using the pseudo-inverse. Okay, so if my command would be vperp, so in the range, then q dot j pseudo-inverse of whatever velocity in that direction would be executed exactly. Now my v has a component also in the null space of the Jacobian transpose, so you can decompose the desired v in gray in a part which belongs to the range and in a part which belongs to the null space of the Jacobian transpose. Pay attention, there's a transposition here. And of course, that part you forget, and the other one is exactly executed. For instance, if I'm putting myself in Q1 equal pi over 6, which is more or less the drawing that I made, so 30 degrees of angle, and I'm assigning a velocity in the negative x direction, so minus 0.50, like the gray one here, I'm computing the solution through pseudo-inverse, and I have 0, 1, 0, 0.1 as a joint velocity. And if I apply this, if I look what is the resulting Cartesian velocity with this joint velocity that I have obtained by pseudo-inversion. So I'm multiplying J pseudo-inverse times V by J, and I get some Cartesian velocity, which is vperp, and this value is minus 1 over 8 square root of 3 over 8, which is more or less the direction of the red vperp vector there. Okay, so this is what I'm getting. If I'm moving farther, if I'm bringing Q1 to pi over 2, so now the robot is stretched and vertical, then I evaluate J, and J is just minus 2, 1, and has all of a sudden a row of 0. And the pseudo-inverse has a column of 0 in this case. And the first column is the pseudo-inverse of the first row, which is nothing else than that row transposed divided by the norm of that row, which is minus 0.4 minus 0.2. Now, using the same V, so I'm still wishing to go in that direction. Now, you should imagine the arm has gone up. The commanded direction is still horizontal in the negative x direction, but this becomes now the range direction of the Jacobian. So this can be executed exactly. In fact, I compute the joint velocity with a pseudo-inverse. In this situation, I have 0.2, 0.1. And if I apply now the Jacobian to this joint velocity, I get Cartesian velocity vperp, which is exactly the desired velocity v. So, okay, I think that this is enough in order to understand what's going on with the pseudo-inverse. Now, everything was said about velocity mapping, but we have seen also in the differential kinematics that we can move our analysis to a higher order, to acceleration, jerk, and so on. So the same thing can be done when we invert things, and we can invert at the velocity level, but also can decide to invert at the acceleration level. And the reason why we're doing this will be clear in a moment. Now, suppose that we have a square Jacobian. you remember the relation at the acceleration. We had r double dot equal Jacobian time q double dot, so the joint acceleration, plus the time derivative of Jacobian times q dot. So now you assume, while for inverting at the velocity level, you assume that you know where you are. So you know the configuration q. With this value, you compute the Jacobian, you invert the Jacobian, multiply by v, and get the joint velocity q dot. In order to do this inversion at the acceleration level, you need more information. You should know where you are in position, so q, but also which is the current velocity that the joints of your robot are having. Why is that? Because you have to evaluate also j dot q dot. So you take r double dot, which is the desired value for your task acceleration. You subtract, so you bring to the same side j dot q dot, and then what is left is j times q double dot, so you invert the Jacobian, as in the first order method. So it's the Jacobian that needs to be inverted. Now, if the Jacobian is non-square, you can use dampedly square or pseudo-inversion. If it's square but it's singular, you have to use the dampedly square, and so on. Okay? But other than that, same story. So you can compute the q double dot. Now, with this q double dot, you accelerate your joint, which were having some velocity and were standing at some position q, and you will get a new velocity and a new position, and so on and so on. You repeat this at the discrete time level in your commands, okay? Why not? You can do this at the third order level. Now, if I bring to one side everything but the Jacobian times the highest order derivative of the joint variable, so j q triple dot, I have r triple dot minus j dot q double dot minus 2 j double dot q dot. We have already commented. So you bring everything you should know on one side, and then you invert the Jacobian, and you get the jerk q triple dot. So in order to compute the right-hand side, now you need to know where you are in position, which velocity your joints are having, q dot, and which acceleration they are having. Now you may imagine, do I have an acceleration sensor? We have already commented that. No, I don't have a joint acceleration sensor. But this can be done at the level of planning. So I'm generating now some evolution of the joints associated to some specification of motion at the task level. So I can compute while moving without the need of measuring things. This is the nominal planning. In fact, we'll see that this is exactly when we're doing trajectory planning in the joint space from a given desired motion in the Cartesian space. Now, as I said, the inverse of the Jacobian, sorry, there's something missing. The inverse, the pseudo-inverse, I made a, that should be a parenthesis pseudo-inverse of the Jacobian, meaning that here you have the inverse, but in case you may have the pseudo-inverse, if the Jacobian is not square, is always the leading term in this inversion. And why do you want to go higher order? Well, the reason is that you expect in this way to generate smoother motion, joint motion. Why is that? Because in fact, you have a command, a Cartesian command, which allows higher order derivatives, so acceleration, jerks, and so on. So you don't have spikes for this quantity. So the Cartesian commands are smoother. If you are in this situation, then you would like to get smoother motion also in the joint space. And so you invert the differential equation at the higher order. Okay? Why smoother? I hope it's clear to you. If you take a bang-bang acceleration profile, so maximum acceleration and maximum deceleration then if you look at the third derivative of the jerk, you have an impulse at time 0, an impulse when you switch from maximum to minimum acceleration, and an impulse when you stop. An impulse function cannot be realized in practice. Indeed, you may have a bang-bang jerk profile, so you will have a linear acceleration profile, a quadratic velocity profile, and you can start from 0 and get to 0, so you can put boundary condition in this higher order case. So as a whole, you have a smoother profiles once you allow the existence of higher order derivative, and then it makes sense to invert at that order.